All right, guys, good morning. So today we're gonna continue doing one last example in this topic that we were covering, basically, relating the accelerations and the velocity and the position. And today we're gonna start an interesting topic, which is polar coordinates and polar accelerations. So in this problem, what we have these two particles, A and B, and what they gave us is they gave us the acceleration of A to be 0.8 t, and the acceleration of B is given to you as 4 meters per second squared. So I want to start by writing the acceleration of A is given at 0.8 t, and then the acceleration of B is equal to 4. All right. So the question is, we would like to find at which time, right, the particles are going to collide. Okay, so as a result of these accelerations, these two particles are going to be moving, and I would like to find out when they will actually collide. So a collision occurred when two objects, right, attempt to occupy the same space at the same time, right? So when they are in the same space, same position at the same time, basically, this is where you have a collision. How can we kind of, formulate that in dynamics, basically, with the tools that we have?
Is their velocity equals to 0 because the velocity vector will then go to the other side?
Right. So they have an initial velocity of 8 meters per second. So initially they have an 8 meter. Each one has the same initial velocity, 8 meters per second, and they are now subject to this acceleration. Think of it like you have an engine or thrust or whatever that is causing this to move at that acceleration. I would like to find out when they will actually collide. Can someone help me out with this?
What was the question?
Okay, what is the question? Okay, so I have these two particles. They have an initial velocity of 8 meters per second, and then each one has its own acceleration. I would like to find what time, basically, these two particles will collide.
Try to find the
For theta
position equation for both of them نحط on equal or لا? In terms of t.
Yeah. Okay. So what should I do now? What should I write here?
ما قريت السؤال بس لي انا ما بعرفش عنه.
مش لازم نلاقي البوزيشن
لا.
Can we find the acceleration AT and AN?
Okay, ATN. Do we actually need AN?
No, we don't need it. We just integrate hold it نجيب الباس S.
Exactly. Yes, we're simply going to integrate these, right? So we have the acceleration of A. I can find the velocity of A. What is the velocity of A?
uh, 0.4 t squared.
Okay, so it's going to be 0.8 t squared over 2, right? Is that it?
Plus 8.
Yes, plus the initial velocity.
Bravo, plus the initial velocity. Okay, so we're good. How about VB?
It's 40
plus
8.
40 plus 8. You never want to forget about the initial condition, right? Then let us find SA. What is SA?
It's
How do you find
0.8 over 63.
Okay, that's right. So you integrate the velocity, right? So it's going to be,
Yes.
So this is 0.4. So 0.4 t cube over 3 plus
8t
That's
plus
it.
S initial position,
which is 0, right?
0.
Okay.
0.
How about SB? I want to integrate this, right?
Yes.
2t squared plus 8t.
Plus 8t. How do I find the time at which they collide?
When they have the
Put
same
them
position,
equal.
SA equals ST.
Each other.
SA is equal to
Doctor,
SB.
shouldn't the initial position تبع SB تكون انه الفرق بين SA و SB مثل ما انهم هلا؟
Bravo, exactly. Yes, you are absolutely right. So I want to see if someone actually see that. So here, if SA is 0, basically A is already at 120 degree offset, right? So basically I have the S position, they would have to be measured from the same frame. In order for me to say that they are in collision, basically, I have to measure the two objects from the same frame. And now basically the two positions is measured with respect to an absolute, are measured basically absolutely as absolute positions. So then I can say it's a collision. So basically SA would have to be measured with respect to this S right here, right? And how do I change that? Basically, I'm gonna have to add here, right? I'm gonna have to add how much? So 120 degree is how much? Pi over 3, right? So this is actually added to SA. So if time is equal to 0, so pi over 3 multiplied by how much? By the radius, مظبوط?
120 مش 2 باي.
مش 2 باي over 3.
Yes, 2 pi over 3. Yep, you're right. So 2 pi over 3, exactly. So 2 pi over 3 times 5, and then another way to convert that, obviously, you divide 120 divided by 180 times pi. So the radian times the radius, basically, that would give me the distance along the arc, right? So if time is equal to 0, SA of 0 is equal to 0. Right? Okay.
Doctor?
Yep. So now I'm going to set SA to be equal to SB, and now I can say 0.40 cubed over 3 plus 80 plus 2 pi over 3 times 5 is equal to 4 t squared over 2 plus 80. All right.
دكتور انت قصدك هون انه عندها initial position.
Exactly. So here SA, if you're looking here, basically SA is measured with respect to this line right here, or this starting point. For you to specify that as a collision, or for you to be able to find the time when a collision will occur, you would have to measure the position of A from the same frame that you use to measure B. So we have to use a common frame for basically measuring the S's. Does that make sense? So here we're basically measuring A from this point. And
Doctor? Doctor?
Yes.
Can you just go up? I need to ask a question.
Let me just.
Okay, continue. That's fine, continue.
So 80 and then 80 will cancel out, right? I'm just gonna bring this guy over here. So I'm gonna end up with 0.4 t cubed over 3 minus 40 squared over 2 plus 1 over 3 is equal to 0. Okay, guys, make sure you don't open your mic if you're not talking, okay? Make sure you stay muted unless you have to talk. So I'm here now. I'm gonna actually have to solve for the time t, right? So there are different ways of doing that. I personally like to use MATLAB, but for your assignment, you are free to choose any calculator that you want to work with to be able to solve that. Okay. Okay, so here you will be able to solve t, and I believe you're going to have t is equal to almost like 0.8, and then t is going to be equal to let me actually quickly solve that so we are all clear on that. Okay, guys, so this is MATLAB that I have here, and I'm gonna basically literally solve this equation. And what I said with MATLAB is I'm gonna have to define a symbolic variable, and I'm gonna define that as t. Okay, it's very simple to solve equations in MATLAB, so I can basically write my expression. Like, let's say f is equal to 2t plus 5 plus 8 times t squared. Okay, so now basically I have the symbolic expression in MATLAB, and if I want to solve it, I will literally type solve f, right? And if I do f, basically it means I'm solving f equal to 0 in this case. Okay, so if I do f, and now basically it's going to solve that. Okay, and then I can do evaluate answer, basically it will simplify that answer even more. So here basically it's a complex number. So let us solve our problem. So how would I solve this problem in MATLAB? So basically, I'm gonna have to actually write that equation. F is equal to how much? So I have 0.4 divided by 3 times t cubed, right? And I highly recommend that you guys start, messing around with MATLAB because it's a very important tool, especially those of you who at some point are interested in kind of, doing masters or later even in your career. You definitely use MATLAB at LIU, but try to master it if you can. So this is my F, symbolic F, right? Now I can actually solve F, right, as a function of time, or I can solve it F equal to 5, 3, whatever it is, basically, right? So here, when I'm doing this, basically, it automatically assumes that I'm solving F to be equal to 0 and as a function of time. So now I got this. So I want to actually evaluate this answer, right? It will basically compute the actual symbolic values of it. All right, so this is what I have now, right? So I have t is equal to 14.6 plus this 8 is minus 16, which is almost 0, right? Which is actually 0, right? And then I have another t is equal to 2.5 seconds, and I have 2 is equal to minus 2.14 seconds. Can someone tell me which value of t which value of t I'm going to have to choose, right? So I have t is equal to minus 2.14. I have, let's call it t1, I have t2, and then I have 3 solutions because I'm working with a polynomial that have an order of 3, right? So you're gonna have 3 solutions. 14.63. And then all these
The
are
smallest?
بس
which one? This one, this one, or this one?
T2.
The 2.5?
2.5. Can someone help me interpret? So what is this value here? What does this
The
value?
second collision, or
Maybe
maybe
the second
third?
collision.
Bravo, exactly. So this is the second. Can someone tell me what is T1? What is the physical
It
interpretation?
doesn't exist. There's no time.
It is where they would have collided.
You can't have time negative, doctor.
What? Okay, someone was mentioning it is what. So this, it's actually, when you are solving. So when you're literally solving a mass problem, right? Obviously, time cannot be negative, right? But these particles would have collided if actually, they were moving with whatever accelerations we had. If they were actually moving, before, right? So basically, we have the solution at t is equal to minus 2.14. So that collision would have occurred like 2.14 seconds ago, right? Given these conditions that we have right now. Okay. Obviously, we're not going to use that, so we're going to simply take this value. Okay. So this is the first collision. Okay. All right, guys. So here we're done with this problem. Okay, now what I'll do is I'm gonna start a new topic basically, which is curvilinear acceleration. And what I'll do is I'm gonna actually start by asking you guys a brief question here.
بس دكتور في نسأل شغله.
Yeah, sure.
Why did they ليش حاطين عليك زيرو انه times exponential؟ ليش بس خدنا اول فاكتور بالماتلاب؟
You mean in MATLAB? Okay, let me just quickly do that.
انه في كان في رقم مضروب باكسبوننشال. ليش انه
Where
تحت اخر شيء الانسرز.
here? Oh no, this is not an exponential. This is like significant figure. So if I do 1 t minus 5, basically it is like 0.0001. Basically, you have 4 significant figures. Okay, this is
okay.
way of writing stuff. Okay, all right, guys. So now let's jump into a new topic, basically, and this is a question I have for you guys. So let's say I'm looking over at Google Maps, and you have a pass, for example, and okay, what is that? We have our dog as well. One second. Okay, all right, guys. So sorry about that. Shit. Okay, yeah. So we have a small dog in the house, so it's not very happy today. Okay, so if I have this frame basically, right, and I gave you this function basically, f as a function of x, right, and basically this is like a road, and I have a car traveling along this road, right? So you could basically now, based on what we've learned, you can find the acceleration using different situations, right? So I could give you x of the car as a function of time, and I could also give you, the y of the car as a function of time, right? If I gave you these two, can you find the acceleration of the car at that instant? How would you find the acceleration of the car? So you have x as a function of time, and then you have y as a function of time. How could you find the acceleration, total acceleration of the car, or the magnitude of the acceleration of the car? Well, you can find v as a function of time, right? It's going to be equal to x prime of t, right? You differentiate x. You guys agree? Which is basically nothing but and then I can also find acceleration as a function of time, which is x double dot t, right? Which is or dv of t over dt, right? Okay, so I can I'm sorry, this is ax, right? So I can find the acceleration in the x direction, and then I can also find ay, right? Which is going to be y double dot of t. So if I do those, basically, we can find ax, and then I can find ay, and then ultimately I can find the acceleration basically, which is going to be square root of what? Ax squared plus ay squared. You guys agree? So this is
هيدي مش AT دكتور؟
I'm sorry.
مش هي بتكون AT؟
No, this is the actual magnitude of the acceleration vector. So if I provided you the position of the object, x as a function of time and y as a function of time, now you can find the Cartesian, the total acceleration based on these two vectors. Basically, all that you need is a orthogonal frame to be able to express a vector. So you have ax, right, and then we have ay. Now we actually have the total magnitude of the acceleration vector. Okay, so on the same thing, right? If I actually told you that this car actually had so a constant velocity v0, right? And I would like to actually find its acceleration at that point. How would you find the acceleration of the car?
بس ليش ما في vy؟
Yeah, you can get vy.
It's only an.
Yeah, I'm only looking at the acceleration. If you want to get vy, it would be y prime of t, right? But here I was simply asking you guys to find the acceleration. So if you want to find the acceleration, you have ax constant. Exactly. So another way of looking at that, so if I told you that the car was actually going, it was a constant velocity v0, right? How would you find the acceleration in that case? What would be at? So now I can actually move into a frame that is here instead of using this Cartesian frame. I would have at, right? And then depending on this, I would actually have an, let's say, right? In that case, what would be at?
0.
0, exactly. And then how about an?
V squared over R.
V0 squared over, exactly, R, right? R at that instant. So if I want to actually find the total acceleration in this case, it's going to be equal to square root of at squared plus an squared. So at is 0 here, so my acceleration is going to be equal to an. All right, so I'm going to actually...
at 0?
at because we said v is constant.
دكتور ليلى at 0.
Here in this case.
اوكي بس نحن قلنا في 0 قد ايه؟ ما قلنا انه هي كونستنت، قلنا انه في 0 ما بنعرف شو هي بعدين.
Exactly. Well, it doesn't matter. Yes, I mean, it doesn't have to be 0. So here at is derivative of v, basically. That's what I meant by that. And then if v0 is constant, then at is going to be 0. But what my point here...
بلكي عندنا انت قلنا انه عندها في 0 وهي دائما سبيد كونستنت تنعكر at equals 0.
So at is going to be the derivative of the velocity along the curve, right? So here, if I told you that the velocity is constant, then at is going to be 0. Well, let me tell you what my point here is. So ultimately, you can also get acceleration to be at squared plus an squared, right? So those two vectors actually have to be equal, right? So no matter in which frame you actually express a vector, whether you have ax, ay, or at and an, a vector is a vector in space. So if I actually have a vector, that vector will actually have its own magnitude. So no matter in which frame I view it, if I view it in this frame, let me actually do that, in this frame or in this frame or in that frame. So if I view it in that frame, I'm gonna get the total vector along I, right? And if I view it like, let's say in that frame, I'm gonna get that vector is equal to like minus 2j, but ultimately the actual magnitude of the vector will always be the same, okay? No matter in which frame we actually express a vector, the actual magnitude will be the same. So here we are doing a mapping, for example, or we're kind of comparing the acceleration between a Cartesian coordinates and what? And basically like a frame that is attached to the curve, which is AT and then AN. This frame basically is kind of moving with the curve. To be able to use AT and AN, you need to know the velocity along the curve, and you would need to know what? You would need to know the radius of curvature at that instant. So if you have these two, then you are good. Okay, so this is what we have learned so far about how we can capture acceleration from different frames. Today we're going to start a new thing. We're going to look actually at the polar coordinate. And again, if we use the polar coordinate, we expect to have the same acceleration or the same value of the acceleration magnitude. So here, basically, we're going to move into a new frame, and then I'm going to call this actually a polar coordinate. So instead of actually having x and then y, right, you could also think. Okay. Another way of actually doing that is I could actually have a vector from the origin to the object that I'm trying to find its acceleration. And then, I'm going to actually define theta. So to be able to actually locate this object in space, I'm going to find this radius or this distance actually to the object, and then that angle theta. But now my frame actually, I'm going to actually have UR. Okay, UR is a unit vector along the R vector that is always collinear with the R vector. All right, and then I'm going to actually have this guy is U theta. U theta, right, is a unit vector that is perpendicular to the radius, and it is in the gross direction of theta. Let me draw this one more time and just focus on this thing. So you have an object basically. Let's say you don't actually have y as a function of x, but actually you have the radius, right? And they actually use that a lot in radar systems. You have a plane going, and basically you're shooting a laser on the plane. You can find the distance from your radar station to the plane, right? And you actually have your this is called the azimuth angle, right? Basically, it kind of locate the angle of your radar gun, basically, that is actually trying to find where. So this is my UR, right? So UR is a unit vector, right, along this guy, and then I actually have what? U theta, okay? And then I can actually now just express this as R. Length R, UR is a unit vector along this distance that is to the object, and then U theta is a unit vector that is perpendicular to R, okay? How can I actually write R as a vector based on what I have here? Can someone tell me? Now let's say you actually have R as a function of time, and you have theta as a function of time, right? So your radar station is telling you, how R is actually changing as a function of time. Like say you have a plane coming in, right? You have a radar now, 2,000 meter, and 1, 2,000 meter, and 2, 2,000 meter, and 3, etc. And your angle theta, it could be 44, 45, 46, 47, etc. You're measuring these as a function of time. How can I now express my R vector basically as a function of these guys? Can someone help me out with this? How can I write R? Okay. I'm sorry? Okay, how can I write R in terms of UR and then U theta and R and theta? How can I write the vector R in terms of these guys?
R cosine theta I.
Okay, that is if you want to express it in that frame, right? If I want to actually express it in the UR frame, it is simply going to be R times UR. Okay, so R is along the UR direction. Okay. Okay, so that is simply mean that I'm trying to express the vector R in terms of this frame. If I want to actually express it in terms of that frame, it's very easy. So I can basically decompose UR into along the X and then along the Y direction. But now I'm interested in finding the acceleration in that frame, okay, in the UR and U theta frame. So if I want to find the velocity, how can I find the velocity vector? You're gonna have to, what? You're gonna have to differentiate.
Derive it.
Gathering data
Yeah, derive
about
it.
this issue
Exactly.
is happening.
You're gonna have
Physicians
to
are gathering data about this symptom or this infection or this virus.
Okay. Okay, I think I have Samir is constantly you're opening your mic, so make sure you don't open your mic unless I actually ask you or you have to talk. Okay. Okay, so my velocity is a derivative of dr dt. So how can I differentiate this expression? Remember, you have R as a function of time. So this is you have to use the chain rule of differentiation, right? So the derivative of this guy is going to be equal to what? R prime.
R prime.
UR.
UR divided by UR prime R.
Exactly. So R prime UR plus R. Now I have to. So is the UR vector changing with respect to time? Yes, it is changing, right? Because you are tracking this object. So the actual vector here is going to change. So it's going to be actually DUR over dt. Okay. Now, how can I find DUR over dt? So what is actually happening, and this is not very easy to know. So this is a vector UR, but that vector is actually being rotated, right? So this is UR at time t plus 1. This is UR at time t. So basically, this vector is rotating in that direction, right? So the direction of it is going to be actually along the U theta direction. As a result of spinning this this vector UR, right, by theta, okay, so the R will not change its direction because it's going to increase along UR. So what theta will do basically will rotate this vector UR, and then it's going to rotate in the direction of theta. So the actual value of this, so DUR is going to be equal to the length of it, which is 1. مظبوط 1 times d theta, right, times u theta. Okay, so this is the rate of change of the vector UR, but now we are differentiating this over dt, so I don't have actually dt on both ends. So dur dt is equal to how much? Theta prime times u theta. Okay, so I'm going to rewrite my velocity vector. So the velocity vector is going to be equal to r prime UR plus how much? R theta prime U theta. Okay, so now.
دكتور في كتاب كيف نوصل للدي ثيتا يو ثيتا؟
Yes, let me just finish that. So here the velocity is equal to what? So the velocity along the UR direction is simply equal to R prime, which makes sense, right? So the velocity along the R, right, is going to be equal to R prime, right? So basically you look into the rate of change of the radius with respect to time, UR, which is very clear. And then on the other end, you actually have R theta prime and theta. So this is a tangential velocity, and then this is a linear velocity. And then both of these will ultimately be a velocity vector along this direction, along the actual direction of the curve. They would have to be.
دكتور أنا ما فهمت كيف جبنا الثيتا برايم يو ثيتا. كيف صارت الدي يو ار اوفر دي تي ايكوال دي ثيتا اوفر تي تايمز يو ثيتا؟
Yeah, sure. I'll be happy to extend that. So here you are. So R is equal to RUR. Okay, if I'm differentiating this thing, right? R is a variable as a function of time, and UR is also varying as a function of time. So these two. Okay, so when I differentiate this, I'm gonna have to do R prime UR plus R UR prime. Okay.
Okay.
And this is what I did: R prime UR plus R DUR dt. So the only thing that may be confusing is how you do DUR dt. So DUR dt, basically here, I'm differentiating a vector. Okay, if I'm differentiating a vector and that vector is not increasing in time and length. So the only thing that will change in that vector is the direction of this vector. And if you see here, basically, as a result of this movement, UR is actually being rotated by theta, and the rotation will actually be along the direction of U theta, always, right? As you are spinning this guy, basically, right? UR is going in the direction of U theta. So you'll have basically DUR is equal to D theta, right? D theta times 1. You know, when you're looking at a very tiny part of a circle, like let's say you're looking at, you want to see this change here, right? Depending on this length, basically, let's say this guy is R. Basically, this guy is going to be equal to how much? R D theta, مظبوط?
اوكي.
Okay, so
ليش اخذنا؟
here R is 1.
ليه؟
Then the length of the UR is 1. It's a unit vector.
اوكي.
So 1 times d theta is d theta, right? Times d theta, that is the direction here. And then I divide by t, basically. I'm going to have dr dt is equal to theta prime theta. All right?
بس مش نحن بس نعمل مش بس نحط انه هاي الديستنس equal r d theta بس مش بس نعمل derivative نعمل dr مش d theta.
Yes, but in that case, we're dealing with the magnitude of the unit vector. So the magnitude of the unit vector here is not changing. It's only 1.
Okay.
All right. So the only thing that is changing about this unit vector is its direction. Okay. So let's. Okay. Now.
That is a function of t هي دائما.
Yeah. Let's get the acceleration before the session ends. All right. So I'm gonna come back here. And I'm going to rewrite this for you guys. So V is equal to R prime UR plus R theta prime U theta. Now I would like to actually get the acceleration. Can someone help me out to find the acceleration?
مش كمان we differentiate V.
Exactly, differentiate V. Okay, what do you get if you differentiate V?
R double prime UR.
Okay.
مش نعمل UV يعني.
Okay. Okay. A is equal to dV over dt, right? And okay, so A is equal to dV over dt. So I'm going to differentiate this. Can you help me how to differentiate this?
So R double prime.
Exactly.
UR, right?
UR, yep.
Plus R theta double prime mu theta.
لحظة شوي, you forgot something here. So UR is changing.
Okay. The like the other one, right?
Yep. So R prime DUR dt. Okay. We'll revisit that. Now we're gonna go here. So what do I get next?
R theta double prime U theta.
Okay, let's start with the first.
R prime, yes. R prime, yes.
R prime theta prime U theta plus what? R theta double dot U theta plus R
theta prime
du theta dt. Okay. So one thing here, we have already established that dur over dt is equal to how much?
R theta prime U theta.
لا, this just theta prime U theta.
Theta prime.
Okay, and there's one more thing I have for you. Du theta dt. Can someone take a guess? What is du theta dt?
R prime UR.
ارجع عملها على الايكويشن يعني هي U over R. U over R.
Right.
over R قصدي.
So what is du theta dt?
مش برجع على الايكويشن تبع اللينكس تبع الارك.
Yeah, so when you are doing dur dt, because UR is rotating in the direction of U theta, مظبوط, basically we're multiplying theta prime by U theta. Now, if you are rotating this guy, how do you think U theta is moving in which direction? So as a result of this, U theta is actually moving in the opposite direction of UR. Can you guys see this? As you rotate this, U theta is basically doing that, right? It's gonna basically fall toward UR ultimately, right? So that
yes.
Okay, so that will actually be minus theta prime UR. So it's like you are rotating this by 90 degrees when you differentiate that factor. Okay. So what I'll do right now is I'm going to substitute whatever that we have here with their values. So now
دكتور كيف ما يو ار ويو ثيتا perpendicular لبعضهم.
UR and U theta are perpendicular, right? But when I differentiate U theta, okay, this U theta is basically falling toward UR as a result of this rotation. So, you know, this is U theta. And then after a tiny rotation like that, that U theta is going to be like this, right?
ايه بس ما يو ار كمان رح تكون perpendicular عليها كمان.
Right. So this vector is actually going to be in the opposite of the UR direction. Okay.
هي مش
So don't worry about it if you don't understand that. So this is, you know, it's not very important that you guys understand these detailed derivations. Okay. What is important is, you know, after I finish that, you know how to apply the equation. This is really matters to me. Okay. But if you think about it, you will actually come in and understand why these are actually that way. So I'm going to actually rewrite these. So I'm going to have R double dot UR plus what is R prime DUR dt? So it's going to be R prime theta prime U theta plus one more time R prime theta prime U theta R theta double dot U theta, and then the last thing is going to be what? Minus R theta prime square UR. So I can actually put the UR alone. If I put the UR alone, I'm going to end up with this guy. R double dot minus R theta prime square UR, and along U theta, I'm actually going to have R theta double dot plus 2R prime theta prime U theta. Okay, so this is the actual magnitude of your acceleration vector. Okay. This is it for this lecture. In the next lecture, basically, in the next recording, basically, I'm going to go over this in detail. So what I'll do right now is I'm going to close this session and then reopen it so we can continue our time.